This video is going to have a lot of vocabulary in terms of relations between x's and y's and whether or not those relations make up a function. So a relation is any set of ordered pairs. The domain is the first piece of the ordered pair, and the range is the second piece of the ordered pair. So we are given an example here. The domain is the first piece, 1, 2, 3, 4, and 5. The range is the second piece, 2, 4, 6, 8, and 10. We can also call the domain the input or independent variable. And a lot of times we call that our x. And if we graph, that's going to go on our x-axis. If we look at outputs, okay, that's the same thing as the range, and a lot of times that's our y. And if we graph, that's going to go on our y-axis. So domain, I used to have an algebra teacher that used to say do is like no. So if you shake your head no, it goes this way for domain. I thought that was really catchy. Now, a function is a special type of relation where every x value goes to only one y value. I like to think of this like a soda vending machine. If I push this button, and I think it's the Coke button, then I should expect out a Coke. If I push the Coke button and I get out a Sprite, that's not what I ordered. So I can't have one button that gives me two outputs. I can only have one button to one output, not two. Now, it's okay to have multiple Coke buttons as long as when I push that button, that's what I get out is a Coke. And then I might have other buttons for other sodas on the other side. We can use this analogy to look also at evens and odds. If I say that my domain is odd or even, and then I try to map that to the numbers 1, 2, 3, 4, and 5. Odd, when I press the odd button, I'm not quite sure what output I'm going to get. However, if I switch these so that the number is the domain, it is okay for me to have multiple buttons that go to odd. So in this case, we say classification is a function of number. Okay, we always say that y is a function of x. If that's the case. Here, not a function. And there's some more examples here in the notes as well. All right, let's look at a price menu piece. Is price a function of time? If I call these my x's or my domains and these my y's, is it true that x only maps to one price? And that is true. Yes. However, if I switch these, I only have two prices, but then I have 3 donuts. Here I'm good, but now if I look at this price, it goes to 2 different outcomes. Not okay. So item is not a function of price in that way. Now, when we use function notation, we use parentheses to indicate the domain or the input. And this can be a little bit confusing because parentheses also mean multiplication. However, right here, we need to make sure that we know that we say that f is a function of a. F is a function of a. So a is our input, f is our output, and a, because it's a function, only gives me one output. If you have something inside your function relation, then we need to use order of operations here. First, add a and b, then apply the function f. You can also think of the function f as an operator, where you have an input and then an output. Using function notation, let's look at a function whose input is the name of the month and the output is the number of days in that month. Let's not include leap years because that just gets confusing. All right, so then January, February, March, April, so on and so forth would go here. And then we only have 3 different choices for our days. January goes to 31, February goes to 28, March also goes to 31. That's okay. You can have multiple buttons that give you the same output. What you can't have is that like April has 30 and 31 days. Then it would not be a function. So in that case, we're going to say that day is a function of month. If I have a function n equals f of y, I'm going to say that one more time, n equals f of y, which is the number of police officers in a town in this year, then let's think about what this means. I'm going to flip this so that it looks like the definition that was given. This is n, which is the number of police officers. This is little y, which in this case is year. So I could say in 2005, there were 300 police officers in this town. All right, our last and final chunk of information on functions is how to plug into function notation. So I want to evaluate this function f of x at these x values. So I'm going to write that as f of 2. And what this means is everywhere I see an x, I'm going to plug in 2. So that's going to be 2 squared plus 3 times 2 minus 4. That gives me 4 plus 6 minus 4, which gives me an output of 6. If I wanted to find f of a, then everywhere I see an x, I'm just going to plug in a. Another way we can say that this is working is we're renaming the variable. Instead of x, I'm going to say it's a instead. All right, let's look at f of a plus h. Now this is where it gets a little bit tricky. Remember, everywhere I see an x, I'm going to plug in so that x equals a plus h. Now, before it said add these first and then apply the function. Well, a and h are two different variables, so I cannot combine them in any way. I'm going to just input them everywhere I see an x. I input a plus h. A plus h squared is a squared plus 2ah plus h squared. I then distribute the 3 and subtract 4. I don't have any like terms here, so that's going to be my final answer for C. Now let's evaluate this equation right here, which we call the difference quotient. All right, notice that in this expression right here, I have the pieces that I've already found in parts B and C of this problem. So in place of f of a plus h, I'm going to put this entire piece that I found in part C. In place of f of a, I'm going to put what I found in part B all over h. That then gives me a squared plus 2ah plus h squared, 3a plus 3h minus 4. So the parentheses just drop essentially on that first one. I distribute my negative on my second, and I divide that whole piece by h. Now in this difference quotient, once you have done that, everything without an h should cancel. That's kind of a check step to know that you did the right thing, is that in the numerator, if it does not have an h, then it cancels. All right, that means I'm left with 2ah plus h squared plus 3h all over h. Now I can only factor, or I can only cancel, excuse me, numerators and denominators when I have a common factor. So I'm going to factor out an h. And now that I have something multiplied in the top and the bottom, those cancel. And my final answer is this expression here.